Well, thank you very much for coming out this evening. I think after this lecture, it'll be my first mince pie of the season. So, we're getting in early. So I'm going to take you on a journey through literature, but from a mathematician's viewpoint this evening. And, it's unfortunate, I think, that often mathematics is viewed solely as something that's useful for science. Of course, it is useful for science. We hear that mathematics is the language of the universe, and that's quite right. The reason for that is because the universe is full of structure and symmetry and pattern, and all those glorious things are what mathematics is absolutely the perfect tool to understand and describe and explore. But we are creatures of the universe ourselves. We enjoy pattern and structure and symmetry. And so it's only natural that those will come out in our creative pursuits, whether that's music or art or literature. So we're going to see in the next little while that mathematics actually emerges naturally in literature in lots of different ways. But the first of those ways, and the one we're going to spend, I guess, the main part of tonight's talk looking at, is structure. So if you were to try and think, where might I find structure in literature? The place where it's perhaps most visible is in poetry. Because while it's quite difficult, perhaps impossible, to give a definition of poetry, we tend to know it when we see it, and any form of poetry will involve some sort of constraint. Whether that's the precise numerical constraints of something like a haiku, an example of this is shown here, with its exactly 17 sounds or syllables. So that's a precise numerical constraint, or other kinds of rule that make a particular poetic form. So you might have, for example, the rhyme scheme. Various forms of classic poetry have different rhyme schemes that tell you which lines rhyme with which other lines. Here is an example of a sonnet. A sonnet has 14 lines, and most sonnets written in English follow the rhyme scheme that Shakespeare used, which you can see, you can sort of have some notation for this, A, B, A, B. That means the lines represented by A rhyme with each other, the B lines rhyme with each other. So we can see that lines 1 and 3 are supposed to be rhyming, and indeed day and may rhyme. Some of the other rhymes you may have to pronounce in Shakespearean English, but yes. So this is a rhyme scheme, and that's a structure that constrains, it gives you some rules within which you can explore and play and create beautiful poetry. And just as in mathematics, those constraints do not stop you being creative. They help you to be creative. They spur your creativity. Within the rules of Euclidean geometry, we can prove Pythagoras' theorem. And within the rules of a sonnet, Shakespeare could write, "Shall I compare thee to a summer's day? Thou art more lovely and more temperate." So these things, they help us to be creative. And within that playground, we can explore and make beautiful things, whether that's mathematics or poetry. So quiz question for you. Which poet has written the most sonnets? So have a think about that. We might think it's Shakespeare, quite a lot of sonnets. I think it's 154 is one estimate I've heard. But that is nothing when you compare to Raymond Queneau, who wrote, well, he produced a book whose title translates as 100 trillion poems, or their sonnets. So how on earth do you fit 100 000 milliards de poèmes, 100 trillion poems, into a book without your publisher getting quite cross? So what you do is you use structure, you use the mathematical concept behind the structure, and you employ combinatorial explosions, is what we could call them. So what he does in this book is there are actually over 10 pages, there are 10 14-line sonnets. So he writes 10 sonnets. Now, each of the sonnets has the rhyme scheme. The French rhyme scheme is slightly different, but that's not important. It respects the sonnet rhyme scheme, the same sonnet rhyme scheme. But then what Queneau does is, in effect, he's created a three-dimensional rhyme scheme, because, as well as this, all of the first lines rhyme with each other, all of the second lines rhyme with each other, all of the third lines rhyme with each other. So he's got this three-dimensional rhyme scheme, which is very cool. Some editions of the book actually help you to do what you need to do next, because what you do then is you can make more sonnets from these initial kind of basis of sonnets by picking any one of the first lines and then following with any one of the second lines and any one of the third lines and so on to make more sonnets. And so here is one edition of the book which helps you to do this. You can literally, the page is cut into strips and you can move and find, make your sonnet, construct it. So then how many potential poems are in this book? Then we can just do some multiplication. There's 10 choices for the first line, times 10 for the second, times 10, times 10, times 10, 14 tens multiplied together. That's 10 to the power 14, which is 100 trillion. Right? So in this book encapsulated are 100 trillion sonnets. Now, I think we obviously get the elephant in the room here, which crops up as a question. This is very clever, but is it clever? Is it art or is it artifice? For me, what makes this be not just a clever parlour trick, it's obviously very difficult to do this kind of thing, create all these interlocking sonnets. What makes it be worthy of being called art or literature is that it raises some really fascinating questions, which are extremely pertinent, in the days of large language models and ChatGPT, about to what extent, firstly, to what extent do these poems exist? To what extent were they written by Raymond Queneau? So we're thinking about whether they exist. If we started right now, drop everything, and start reading one of these sonnets every minute, and when we're done, we can have our mince pie, we might have to wait quite a while. Because I'm sure you quickly calculated in your head, if you read one of these sonnets every minute, we will be done after 190 million years, roughly. We're not taking any breaks here for sleeping and eating and things. So nobody could even read all of these sonnets. The human race is not going to read all of these sonnets. Raymond Queneau has not read all of these sonnets. So how can you have authored a thing if you haven't read it? But he has written every single word of every single line of every single one of these sonnets. So he has in some way written them. Have we written them if we make the choices? What's our contribution? We didn't write any of the words, but somehow we put them together. Or if we chose randomly and got a machine to choose, has that machine written this sonnet? So I think it's just very interesting way and lens through which to view some of these questions that are broader than this collection of poems. So yeah, I love this idea, and it's very well executed. There are translations of this as well, which is even more of a feat, I think. So that's one way in which, if we see that there's a structure, we can use mathematical ideas to make something interesting. I want to give you another example of a structure in poetry, and this is a different kind of poetic form. It doesn't have a rhyme scheme. So instead of a rhyme scheme, what's it going to have? Well, it's a sestina. So in a sestina, there are 6 stanzas, and each stanza has 6 lines, and the end words of each line. So you see the first stanza of my favourite sestina here by Elizabeth Bishop. Those end words are used in every stanza, but in a different order. And the ordering changes from one verse to the next in a prescribed way, in the same way every single time. And it's this beautiful spiralling, corkscrew-like permutation of those words. And I'll show you what it is. So if the end words are like 1, 2, 3, 4, 5, and 6, what you do is you start from the end and work backwards, 6, 5, 4, and you interleave with starting from the beginning and working forwards, 1, 2, 3. So the order you get is 6, 1, 5, 2, 4, 3. And if we try this out for our example here, so the end words there, coffee, crumb, balcony, miracle, sun, river. I should say at this point, we're talking about this poem and sort of analysing the structure of it. It's a beautiful poem, which if you haven't read it before, do go and read it after the lecture, because I'm not doing it justice here, just going coffee, crumb, balcony. But it's a wonderful poem. These are the words in the order they appear in the first stanza. So we can apply this permutation. So we start at the end, river, and then beginning coffee, and then sun, and then crumb, and so on. And we get this order. So river, coffee, sun, crumb, miracle, balcony will be the order of the words in the second stanza, those end words. And you can see that's the second stanza. There they are in that order. So this is this rule that says what the end words are going to be, and then you create your sestina. And these words, it's like a tolling of a bell. They keep recurring, but in a slightly rearranged way. And the sestina structure is very beautiful because every word, it turns out, in the 6 verses that there are, every end word appears at the end of every line exactly once. That's very nice. There's another nice thing, which is, okay, by the time you get to the very last verse or stanza, we're at this ordering that you can see. So crumb, miracle, river, sun, balcony, and coffee. So that's the final stanza. If we were to repeat this permutation one more time, we would get, well, we can work out what we get, start at the end and work backwards and interleave with starting from the beginning, working forward. So we get coffee and then crumb and then balcony and then miracle and then sun and then river. This is what we get. And if you look super carefully, you notice we've actually retrieved the order that we started with. So these 6 verses are kind of the complete set of all the possible orderings that we can get by applying this permutation. If we were to do it again, we get back to where we started from. So it's got this lovely completeness to it. 6 verses, 6 lines in each verse, 6 end words. Every word appears exactly once at the end of each line. And when you're done, if you were to repeat, you get back to the beginning. So that's really nice, complete, lovely structure there. I should say, typically in a sestina, what you do is then you tie it up with a bow by adding 3 final lines, just to sort of finish it off, and all the end words appear somewhere in those 3 final lines, just to say, and we're done. Now, we can look at this and say, this is a really lovely structure, but I would really like to write a quintina. Can I do that? Can I write other kinds of ina? What's our favourite number? It's n. Can I write an n-ina? And mathematicians thought about this in the 1960s. Can we create new kinds of literary forms using our maths powers? So what would that mean? That would mean kind of like a sestina, the same permutation, but we want n stanzas of n lines. So for instance, let's say we want to write a quartina, 4, n equals 4. Can we do this? Well, let's imagine what 4 end words what comes in a set of 4? Let's say the end words are north, east, south, and west. And let's do this permutation, this spiraling permutation. So we go to the end and work backwards, so west, and then north, and then south, and then east would be in the second stanza. Those would be the end words. Now already it's not looking great because south hasn't moved. So already not very happy with this, but okay, let's plow ahead anyway. Do this again. What's verse 3 going to look like? Well, it'll be east and then west, and then south and then north. South again hasn't moved. Not great. That's verse 3, stanza 3. What about the final 4th stanza? Let's see what that would look like. Well, we do this again, this spiraling thing. So north and then east and then, oh no, south and then west. Unfortunately, we've got back to the beginning too soon. We've retrieved our initial ordering after only 3 verses. So this is a total failure. This does not work for n equals 4. We get a horrible thing that we've only got 3 verses and one of the words never gets to move around. So this is a failure for n equals 4. So it doesn't always work. It works for 6, and there's been research and mathematical papers out what values of n does this work for. I'm not going to give you the full details. You can look that up, or I can send you a reference if you need one. But there is a particular kind of number, which is a lovely kind of number, for which this is guaranteed to work, where you can write an n-ina. Now what I'm about to say, this gives you some numbers that definitely work. It's a sufficient condition, therefore it is not a necessary condition. And here it is, and it's related to this brilliant mathematician, Sophie Germain, who, French mathematician, working at the end of the 18th, early 19th century. She worked on lots of things, but one of the things she was trying to do was to prove Fermat's last theorem, at least in some special cases. And one of the cases she managed to prove it for, kind of the exponents, the powers, the numbers that you're working with, are kinds of prime numbers that are now called Sophie Germain primes. And so n is a Sophie Germain prime if both n and twice n plus 1 are prime numbers. These things have lots of applications actually, but this is my favourite application, obviously. So 3, for example, is a Sophie Germain prime because twice 3 plus 1 is 7 is also prime. 7 is not, because twice 7 plus 1 is 15, which isn't prime. Okay, so if your number is a Sophie Germain prime, then you can write an n-ina. So you can write a tri-tina, and I've seen some of those in print. However, good news if you want to be a literary pioneer, I have never seen a 23-ina. So if you want to be the first there, be my guest, because 23 is a Sophie Germain prime. So we know that the structure will work for n equals 23, and lots of other numbers. So that's a really cool kind of interplay, you know, this question that comes from poetry, and we can ask ourselves interesting mathematical things about it, and then you can feed back and say, look, here is some stuff, maybe not 23 Inas, but look, there are some other variants of this structure that will work, and the mathematics can prove that for us. So that's very cool. So we've talked about some poetry examples, and for obvious reasons, because structure is nearest to the surface that we can see it in poetry. But it's very far from the only place where there's structure in literature. Lots of novels and works of fiction use structure. In fact, I would say they all do. Because really, what have we got? What is making up a book? Well, we've got the whole book, might be split into chapters or not. Those chapters might be split into paragraphs or not. Paragraphs are made up of sentences. Sentences are made up of words. Words are made up of letters. It's like the kind of point, line, plane of geometry. At every stage, the author can choose to have some kind of constraint or restriction or structure. And so it's not about, is there a structure? It's about what structure you choose, just like in mathematics. Which axioms are we going to use? So there are, for example, books which are called what are called lipograms. They omit one or more letters. In other words, they never use one or more letters of the alphabet. Famously, the book La Disparition does not involve the letter E anywhere in it. So that's a restriction, a constraint on the level of letters. But I want to talk about a book that has a particular kind of rule about its chapters. So this came out, I guess, 10 years ago. It won the Booker Prize 10 years ago, 2013, by Eleanor Catton, The Luminaries. It's a brilliant book. It's got everything you could want in a book. It's got love, betrayal, murder, stolen gold, opium, all sorts of things in this book. It's a great story, and it's set in a gold rush town in New Zealand in the 19th century. One of the major themes of the book is the interplay between chance and fate and destiny, and how much we are in control of what happens to us in our lives and how much we're just being buffeted around by outside forces. To tie in with that, there are lots of references to astrology, and astrology plays a part in the structure. That's not the mathematical bit, obviously, but so she has 12 characters, which are very important. Each of them is sort of loosely tied to one of the signs of the 12 signs of the zodiac. And the luminaries of the title, that's the sun and the moon, they are the lovers in the story. So there are these kind of astrological themes, and that is again sort of playing into this, how much are we in control, or are there other things that are controlling us? But the mathematical thing in the book is the structure of the chapters. So there are 12 chapters or sections in this book, and each one is half the length of the one before. So the 12 kind of mirrors the idea of the astrology themes. The halving is like the waning of the moon, and it gives you it's really fascinating reading this book. You do pick up on this. You may not instantly realise what's going on, but the chapter's getting shorter and shorter, and we can look at what that does kind of visually. Here's the first chapter. Here's the second one, half as big. Third one, fourth one, 5, 6, 7, 8, 9, 10, 11, 12. And, you know, one could go on, but you can see what we're creating here is this lovely spiralling in effect. You can already tell just from this picture that the first chapter is more than half the book, right? Everything else fits into an area smaller than that first chapter. If you're a mathematician in the audience, you might want to work out where this is converging to in the square. But this picture also is a guide to the experience of reading it. You feel that, you know, that the action starts to pick up in pace. Events are kind of hurtling forwards towards the end, but the key characters, these luminaries, their actions, their future, their fate is kind of closing in on them. You can feel the gears are turning, and by the very end, that very last final chapter, which is just a short conversation between the two lovers in the book. It's not chronologically at the end of the book, but it's in the end, final chapter. You know that their fate is sealed, and they don't, and it's because they have been hemmed in by this beautiful spiral. So that's what the structure does. But I've said that very last chapter is the shortest chapter. Now you've got to be careful how long you make that very last chapter, and I want to show you this, we can work out, just knowing that the lengths are halving every time, we can work out the total length of the book in terms of that very last chapter. And this will tell us how careful we need to be about the word count of that last chapter. Let's suppose it has length S, let's say S for shortest, then the one before has length twice S, and then 4 times S and 8 times S and so on. We have to do 11 doublings to get back to the first chapter. So the first chapter has length 2 to the power 11 times S, which is 2048 S. Okay, so we can then work out the total length of the whole book. So already the first chapter is more than 2,000 times as long as the last chapter, right? So you've got to be careful. The total length of the whole book we can find by adding up all of these chapter lengths, right? Now, there's a lovely trick, which you may know for adding up things like this. It's called a geometric progression. What you do is you don't do it. You leave this for a moment, and what you do is you double this whole equation. This works more generally, but just to show you this. So you double the whole equation, and we now get twice the total. This looks like it's a silly thing to do, but it isn't. You double this equation, and you then get 2s, 4s, and so on. And right at the end, that 2 to the power 11 is doubled to 2 to the 12. Now, the reason we've done this is because on the left-hand side, we're going to subtract the top equation from the bottom. On the left-hand side, we're going to get t again. 2t minus t is just t. That's our total length. That's the thing we're interested in. On the right, loads of stuff cancels out. Yeah, this is the trick of finding the sum of a geometric progression. For the mathematicians present, you will recognise having done this. So lots of things cancel. The 2s's cancel, the 4s's cancel, everything cancels all the way to the end, except for the very last term on the right-hand side in the bottom equation and the very first term in the top equation. And so you get this lovely simple expression that the total length of the book in this case is that shortest chapter length multiplied by 2 to the power 12 minus 1. Very nice. We didn't have to add up all those numbers. So why have I gone through this little calculation? Well, we can see from this that 2 to the power 12 is crucial to the structure of the book, right? It's at the heart of what's going on. And again, one might say, well, we're having fun doing this, but we're mathematicians, and maybe Eleanor Catton doesn't need to know this to do, to use this structure in her book. In the case for the defence, I say, absolutely, yes, she does. She's interested in this, and I can prove that she knows about this. She knows 2 to the 12 is vital for the structure. And here's why. Here's how I know it. So in the book, I mentioned there was some stolen gold. There's a court case, and the exact monetary value of that stolen gold is given. And it's £4,096. So if you are familiar with your powers of 2, 4,096 is 2 to the power 12. So she's put that in there. It's a friendly little, hey, look, see, this is what I'm doing here, 4,096. Any mathematician reading that book goes, oh, it's interesting. Maybe there's something going on here. Yeah, so it's there. That stolen gold, that 2 to the power 12 pounds worth of stolen gold is hidden right here. It's sewn into the fabric of the book, there for us to find. So that's really lovely. I'm going to give you another example of a book that is based on a mathematical structure now. And this is a slightly more intricate mathematical structure, but it's really beautifully done again. But the story of this structure, we have to go back a couple of hundred years, and we have to look at a card puzzle that was racking the brains of the well-to-do French in about somewhere in the early 18th century-ish. So what you do is you get a pack of playing cards, and in a pack of playing cards there are 4 suits. You've got spades, hearts, clubs and diamonds. And what you do is you take the highest valued 4 cards from each of those 4 suits. So the Jack, the Queen, the King and the Ace. So that gives you 16 cards. And what you then have to do, the challenge is to arrange them in a square, a 4x4 square, so that in every row and in every column, there's exactly 1 card of each suit and exactly 1 card of each value. So in every row and in every column, there's 1 diamond. In every row and every column, there's 1 king, let's say. And kind of implicit in this puzzle, because you're playing with a physical pack of cards, implicit in this is that every combination, every pair appears exactly once. So there's, unless you're a cheat at cards, there's only 1 ace of spades, right? So each combination of those 2 kinds of thing appears exactly once here. So this puzzle is I mean, that's one solution, but I haven't ruined it for you. There are lots of other solutions to find. It wasn't, though, until the 20th century when the British mathematician Kathleen Ollerenshaw classified all of the solutions to this problem, and there are, I think, 1,152. You can check that on the way home. Just work them all out quickly on the bus home. But this is one solution, but there are others to play with. However, once you find a few solutions, maybe you need a bigger challenge. So a bigger challenge came about in the 19th century in the Russian imperial court in St. Petersburg. And everyone was going mad trying to solve the 36 officers problem. So this problem is like the 6x6 version of the card puzzle. This one, you have some army officers, and there are 6 regiments, and in each regiment 6 ranks. So you have 36 officers in total, 6 from each regiment, 6 of each rank. And you have to arrange them in a 6x6 array so that in every row and in every column, there is exactly 1 officer of each regiment and 1 officer of each rank. And no pair is repeated twice. So you can't have like 2 generals from regiment 1 or something. So every possible pairing occurs exactly once. So this is the challenge. It's just the 6x6 version of this card puzzle. And nobody could do it. Catherine the Great couldn't do it. Empress Regnant of all Russia could not do it. So this became then a big talking point. You might have sort of noticed it's a bit reminiscent of a puzzle that actually lots of us do every day. It's a bit like a Sudoku. It's not the same, but it's a bit like it, because a Sudoku is a kind of one set version of this, because the numbers here in Sudoku, you've got the numbers 1 to 9 appearing in a 9x9 square, and every number appears exactly once in each row and in each column. There's an additional requirement about the blocks, we won't worry about that, but it's sort of reminiscent of a Sudoku. Sudokus are examples of a kind of structure called a Latin square. And that is where you have a set of things in a square such that there's 1 of each in each row and column. So what we've got here with our card puzzle and the 36 officers is kind of you've got 2 Latin squares at the same time. Because in the cards, you've got the Latin square of the suits, 1 heart in each row and column, 1 spade in each row and column, so on. And you've also got the Latin square of the card values, 1 queen in each row and column, 1 king in each row and column, so on. So you've got 2 Latin squares going on at the same time, but with a specific requirement. Every pair must occur exactly once, right? 1 ace of spades. So a setup like that is called a pair of orthogonal Latin squares. So what we've got here to solve this card puzzle, we are finding, what we're really being asked to do is to find a pair of order 4, so the size of the square, orthogonal Latin squares. And the 36 officers would be an order 6 pair of orthogonal Latin squares. Right, so Catherine the Great cannot find orthogonal Latin squares of order 6. She doesn't know that's what she's trying to do, but she can't do it. No one else can. So she asks a passing mathematician who happened to be visiting Petersburg at the time, and to her great good fortune, it was Leonhard Euler. Leonhard Euler. So annoyingly, I've revealed the punchline of this, but before I wanted to. But look, there's Leonhard Euler. He's puzzling over this. He can't find this. He can't solve the 36 officers problem either. And so when Euler can't do a thing, you listen, because he's very clever, one of the greatest mathematicians of all time. But of course, immediately, he sees what the structures are. He actually calls them Greco-Latin squares, because he writes, there's 2 different sets involved. He writes 1 in Latin letters A, B, C, D, 1 in Greek letters alpha, beta, gamma, delta. And then he calls these structures Greco-Latin squares because of that. Actually, Latin squares seems to be a back formation from that. They're now called Latin squares because of this Greco-Latin square thing. But he asks, can we make these things of any size? And if we can't, what sizes can we do it for? And so he could do the n equals 4, that's the card puzzle, and he worked out how to do all multiples of 4. He could do it for odd numbers. You can't do it, and a moment's thought will convince you cannot do it for a 2x2. It just doesn't work. You make too many requirements on each individual square. So you can't do it for n equals 2. 36 officers problem, he couldn't do it, thought it was impossible. And so he had these numbers that were like 2 more than multiple of 4 that he couldn't do. And so that was his conjecture. You can do it for all numbers, except when you're 2 more than multiple of 4, which 2 and 6 are examples of. And so, it's a great surprise to the world, when in 1959, 3 mathematicians found order 10 orthogonal Latin squares. So 6 is indeed impossible. That was proved finally, gosh, in about 1905, I think, by a chap called Gaston Tarry, who did a, well, aptly named proof by exhaustion to show that it couldn't be done. But 10, so that was impossible. So everyone's like, yep, Euler's right so far. He's always right. So in 1959, when this happened, it was a huge surprise. And this made the front cover of Scientific American in November 1959. These orthogonal Latin squares of order 10 had been found. It was like, wow, Euler's never wrong. He was wrong. And it turned out, in fact, that you can make all of these other numbers. Only 2 and 6 are impossible. So this is a really surprising thing. And this discovery was still then relatively recent and exciting when, in 1978, Georges Perec used these orthogonal Latin squares of order 10 as the basis for the structure behind his book, Life, a User's Manual. And it is set in a Parisian apartment block with 100 rooms in a 10 by 10 configuration. And every chapter is set in a different room. And the Latin squares are used to give each chapter its unique flavour. Because what he had lists of kind of 10 attributes. It might be colours or kinds of fabric. And he used the orthogonal Latin squares to make it be that every combination would appear in exactly one chapter. So exactly one chapter would have, I don't know, red silk, and exactly one chapter would have green velvet, right? So he uses this to give each chapter a special flavour. The book, one of the themes of this book is failure. There are characters who are trying to do things. There's someone who's trying to do lots of different jigsaw puzzles of different places around the world, and he dies before he can complete the last piece of the last puzzle. There's lots of things like that going on. So what better structure to use than, the one, almost the only example of Euler's failure to predict these structures. There's other structure. The stories follow a knight's tour of a 10 by 10 chessboard. So which chapter comes next, which room it's happening in, you're following a knight's tour of a 10 by 10 chessboard. But remember, this is a novel about failure. There's only 99 chapters. The knight's tour is never completed. And look at the excuse that Perec gives. He blames the little girl on pages 295 and 394 for this oversight. So it's really just a fun thing with this wonderful mathematical structure underneath it. Okay, so we're following a luminaries-like structure for this talk, so don't panic that I've only talked about structure so far. We're going to talk about other ways that mathematics can appear in literature, but not at as great a length. So that's lots of different structures, and it's really cool, and they're there to be found. But there's another way that mathematics can make itself known, and that is in the words that are used, and in the symbolism, the metaphor, the imagery. And you see mathematical ideas from our most kind of basic type of story all the way up to, Tolstoy talks about calculus in War and Peace. So when I say our most basic kind of story, what did we all grow up with as little children? We had fairy tales. Fairy tales, folk tales, religious texts use the same symbolic numbers over and over again. So here's just a few examples. You've got 3 bears whose porridge Goldilocks steals, 7 dwarves, 12 dancing princesses. 3, 7, and 12 crop up over and over again in these kind of very simple stories. And there are other numbers too, and one could discuss them. There's a whole chapter on it in my book. Read my book. But 3, for instance, really, really kind of profoundly part of the structure of narrative more generally. We think of 3-act plays. Stories have a beginning, a middle, and an end. If you have a collection of books, it's most often going to be a trilogy. But then number 3 in fairy tales, there's a really kind of, I feel almost a geometrical reason why 3 happens so often. You get 3 wishes. 3 brothers go on a quest. There are 3 billy goats gruff and 3 little pigs and 3 bears. Why? Why is this? So here's my suggestion. And it's really about geometry. 3 brothers go on a quest. We all know what's going to happen because we've heard lots of fairy tales. The first brother thinks he's so great, he fails. Right? That's a single data point. Here it is. We've got nothing to go on. Second brother thinks he's also great. He fails. Now I've got 2 pieces of information. 2 points give us a line. They give us a direction of travel. We know what to expect now. When the third brother goes along, of course we know he's not going to fail. with 3 points now allow you to go up a whole dimension. They are the smallest number of points you can draw to create actually a shape. And in narrative, it's the smallest number of kind of repetitions that allows you to create a pattern and then subvert it and surprise the listener. So this, for me, is why 3 is a vitally important part, both of geometry and of narrative. So that's at the most kind of elemental level of story. But we can see that mathematics, pieces of imagery and metaphor and symbolism, mathematical, just all over literature. And some authors in particular really just enjoy mathematics, right? They like it. You can see that they like it. Herman Melville is like a classic example of this. He just drops mathematical ideas into his books. And it's because, right, they're part of the furniture of his mind. This is my view. If you can't read a book like Moby-Dick without thinking Herman Melville enjoys mathematical ideas, because he just drops them in, like he would with other pieces of imagery. It's just what he wants something to show us, to describe what he's looking at. What shall I do? The mathematical idea comes to mind. I'm just going to mention one example of this in Moby-Dick. So as you remember, Moby-Dick is the story of Ishmael, who takes a job as a deckhand on a whaling ship called the Pequod because he feels like seeing the watery part of the world. And Captain Ahab is his boss, who kind of conceives an animus against this whale, Moby-Dick, and that, you know, things don't, I don't want to spoil it, but things don't go absolutely according to plan. However, it's a wonderful book, and you know, you should read it. You'll enjoy it if you haven't read it already. So Ishmael, he's on this ship and he sort of daydreams. There's lots of quiet moments. You're not always harpooning whales. There's quiet times, and often he has little thoughts and he daydreams and he meditates and he thinks, and quite often those thoughts are mathematical. One example involves a beautiful mathematical curve called the cycloid. So here is the cycloid being made. Just a very simple idea. You roll a wheel along a road and you follow a point on the rim of that wheel as it rolls, and you want to know what curve is that's being produced. We call it a cycloid. Galileo gave it that name. And it's a lovely, lovely, beautiful curve. It's got many fantastic properties. It's incredibly beautiful, and it got the nickname the Helen of geometry. So all of these people and many others, like every mathematician you've heard of from the 17th and 18th and 19th centuries, have studied the cycloid. Here, this is a statue that's in the Louvre of Blaise Pascal. He's studying the cycloid. It's probably hard to see, but that tablet that he's looking at has a cycloid on it. It got this nickname, the Helen of geometry, because of its beauty. But there was also another reason. It's because it caused, like Helen, some squabbles from time to time. Let's call the Trojan Wars a squabble. But people would argue about what's the best way of proving this particular thing. Descartes and Fermat had a big spat. I think it was Descartes who said that Fermat's work was ridiculous gibberish, which is, you know, not quite standard academic language. There were priority disputes. Who had thought of this thing first? But the beautiful properties include, and they're really just lovely, the area under one of these cycloid arches is exactly 3 times the area of the circle that makes it. Christopher Wren, who's in that list, some people think he's famous as an architect, but really he's a mathematician who would take him for mathematics. He was the first to find the length of the cycloid arch, and it's exactly 4 times the diameter of the circle that makes it. Lovely, lovely. And there are other beautiful properties and unexpected properties of this curve as well. And it's one of these unexpected properties that Ishmael just alludes to, just sort of drops it into the conversation. He's got a boring job that he's doing. He's cleaning out the tripods. The tripods, these great big cauldron-like vessels they have on board ship, which they use to do a very messy job rendering down the whale blubber to get oil. And it's really horrible and messy, and then you have to clean them. And so he says it's a place for profound mathematical meditation. It was in the left-hand tripod of the Pequod, the ship, with the soapstone diligently circling round me, that I was first indirectly struck by the remarkable fact that in geometry, all bodies gliding along the cycloid, my soapstone, for example, will descend from any point in precisely the same time. So this is very cool. This is what he's talking about is called the tortichrome problem, which is to find a curve so if you just have it, you know, everything's a smooth curve and a particle and no friction and all that stuff. But if you have a particle on this curve and you release it, from whatever height you release it, it will reach the bottom in the same amount of time. Now, there's no reason to even think that's possible, but it is, and the solution is a cycloid. And it's one of these wonderful things in mathematics where something you've encountered in a completely different area suddenly helps you out when you're trying to, as Christian Huygens was when he thought about this, trying to make a better clock. So this is the solution to the tortichrome problem. It's fantastic. I love cycloids. But this is an example of kind of a metaphor, a bit of symbolism in Moby-Dick. There are loads of them. They just crop up in the story. But there's lots of examples of books where there's a sort of running metaphor with something mathematical. And one of these, which I will just mention briefly, is Life of Pi, right? So obviously pi is in the title, but of course, if you read this book, you know that Pi is Pi Patel, this young boy who there's a shipwreck and he gets stranded with a Bengal tiger in the ocean for months and months. It's a beautiful, amazing book. But okay, Pi Patel is not named for the number pi. He is named because his uncle is a fanatical swimmer and he's always going on about this brilliant swimming pool, the Piscine Molitor. And as a result, this young baby gets named Piscine Patel. Now, if you go to school and your name is Piscine, it's not, what were the parents thinking? So at some point he gets fed up of being teased and says, no, my name is Pi. Everyone's going to call me Pi from now on. He writes the letter Pi on the blackboard and he says, this is my name now. And in that Greek letter that looks like a shack with a corrugated tin roof, in that elusive, irrational number with which scientists try to understand the universe, I found refuge. But this isn't where it ends, because all the way through the book, there's this really fun interplay between thinking about the number pi and thinking about the boy, Pi Patel. One example. So pi, the number, he says there, it's irrational. So it goes on forever. As if you try and write it as a decimal, it goes on forever, never repeating any patterns. And irrational means you cannot write it as a fraction of two whole numbers. So that's what it means mathematically. But the boy, Pi Patel, he has this adventure and he's on this boat for months and months and he has all these curious experiences. It's really a dreamlike experience. And there's this constant question of, to what extent is what he's saying real? Is it imagined? How much of this can we believe? Is pi rational? It's sort of a long-running little thing through the book, very playful idea. But there are other things. So Pi Patel says, I hate to bodge an ending. I want to finish my story. And he's frustrated that his name and the number pi doesn't finish. It goes on forever. You can never know the end of pi. So he would like to finish his story. He says, can I finish my story in exactly 100 chapters? Well, Jan Martel allows him to do that. The book is 100 chapters long exactly. But there's another number in the book that is mentioned specifically. And I was interested in why, that when someone uses a specific number, like that 4,096 earlier, it's interesting to say, have they done that for a reason? And the number is the number of days that Pi Patel is on this boat with the Bengal tiger, incidentally, whose name is Richard Parker, which if you're a pure mathematician, there was a mathematician called Richard Parker who was like one of the key important people in the classification of finite simple groups. That's a coincidence, sadly. I think that's a coincidence. So that isn't one of the themes. Right, so this number is how many days they were at sea. And Jan Martel was interviewed a few years back, and he said, actually, this iconic, the tiger, at one point, it wasn't going to be a tiger. He was trying to decide what animal to use. He thought of a hippopotamus, which, can you imagine? There's a hippopotamus. And then he said, I realized that wouldn't work because a hippo is a herbivore. It wouldn't be able to stay alive for that length of time at sea. So I decided I was going to have a tiger. So the number of days, the length of time, is more important than it being a tiger, right? So what is this number of days? Well, it's 227. Now that doesn't seem like anything, but then I thought, right. Pi is irrational, but we know that any irrational number can be approximated as closely as we need to by a fraction. And one of the most famous approximations to pi is 22/7. So I'm like, he's just given us he's given us a rational-ish version of pi in that, just a nice little thing for us. So that's really cool. So that's Life of Pi. And again, there's just these little references to pi throughout, which make it even more fun to read. The very final way, and in our halving and halving structure again, I'm going to spend half the time on this final way that I did on symbolism, is sometimes mathematics is right in the forefront of the story. It's sort of openly there, and sometimes you even get mathematician characters. Now, okay, we can give examples of these stereotypes, you know, oh, the tortured genius, the child prodigy, the being of pure logic who's just there to advance the plot by inventing the ramified functors of the 9-dimensional asymptotes or whatever. String some random words together and then you can travel in time. But sometimes, and I'm just going to mention a couple of books to finish off with, where there are mathematician characters and mathematical ideas that are presented in a really interesting way. And almost this is like, go away if you haven't heard of this already. And go and see the play Arcadia by Tom Stoppard, or indeed anything that Tom Stoppard has ever done. But this is my favourite of his plays, or read it, because it's just, it's an exuberant, joyfully, openly mathematical play. It's got this wonderful character, Thomasina Coverley. It's sort of between the present day-ish and, gosh, 1809, I think. And she's this young, aristocratic young lady. They're in this big big country house. She's brilliant at mathematics, but she's not, you know, a tortured genius. She's just a fun, brilliant, exciting, excitable young girl who loves mathematics and is good at it. And there's lots of fantastic mathematical ideas in here, everything from Fermat's last theorem to, you know, fractals and everything in between. She's got this great idea to invent a new geometry of irregular forms, she calls it. She says, in mathematics, if we can have a bell curve, why can't we have a blue bell curve? And she tries to work out what that would be like. And we know, sort of looking back, she's sort of trying to invent fractals, but, you know, there were no computers at the time, so it couldn't be done at that time. So she's fantastic. Some people have said, you know, aristocratic young lady who's really good at maths at the start of the 19th century, could this be Ada Lovelace in disguise? Tom Stoppard has said no, so we're not allowed to think that. Stop thinking that. But, you know, there are some echoes maybe. But if you want to read the absolutely definitely true story of Ada Lovelace, look no further than The Thrilling Adventures of Lovelace and Babbage, one of my favourite graphic novels by Sidney Padua, which tells, as she says, the mostly true story of the first computer. So in this version, the two of them managed to actually build the analytic engine and use it to fight crime, which of course is awesome. So yeah, there are sometimes real mathematicians featured in books, you know, with various levels of actual verisimilitude. Just to finish, in like one more minute, the last example I want to give, I think is a very important type of mathematician to have in a story, and it's the mathematician who just happens to be a mathematician. They're like a person. It can happen. They're a person. And this is just, I think it's just so important to say, we mathematicians, we come in all varieties, but we're people, and we can also have, you know, our stories do not have to revolve entirely around mathematics. For example, Odenigbo in Half of a Yellow Sun. So this is Chimamanda Ngozi Adichie's wonderful, powerful 2006 novel about the Biafran Nigerian civil war. There's the movie poster there. And the character of Odenigbo, he's a mathematician. He's a professor of statistics at Nsukka University in Nigeria. But that's his job. But he does talk about liking mathematics, and he mentions some mathematicians and some of his work. But that isn't the whole thing about him. He's not there to be a mathematician to invent something that helps the plot along, or to have some sort of tragic situation because he can't stop thinking about differential equations and his wife. That is not his role in this book. He is a mathematician, but he's everything. Like, he's flawed, he makes mistakes, he does good things, he does bad things, he's brave sometimes, he's not brave other times. He's a fully three-dimensional human being whose job happens to be professor of statistics. And I kind of thought, well, this is actually fairly unusual to see this, and I wondered what, you know, was behind this choice of Adichie. So here is him coming back after the war, finding his old papers. He talks about some of this paper that he finds on rank tests. And I thought, oh, I wonder if is that a plausible title for a paper? And so in trying to work this out, I found out, or, you know, that her father, Chimamanda Ngozi Adichie's father, James, was a professor of statistics at Nsukka University in Nigeria. Right? So, of course, with similar sounding paper titles. Now, I'm not saying this is her fault, you know, we're not being reductive. But I think what this does for her is she has grown up then around people who happen to be mathematicians, right, including her own father. And I think, so this is, just, you can see this is a very human portrayal of this person. This isn't her father, that's not what her father is like. But you know, the fact that this character is a human being who happens to be a mathematician, this is something she has seen with her own eyes. So that's where we're going to finish. I hope you know we've seen there are many ways that mathematics can show itself in literature, from the very basics, the foundations, the structure, then the words and the imagery and the symbolism, right through to the plot and the characters in our books. So I hope you've enjoyed it. Thank you very much.